Hello everyone, welcome back to Stationeers. We are back working on our main base, and last time we got these beautiful airlocks set up. Now, I know last time I was talking a little bit about maybe redoing some of our atmospherics setup out here. And it still does need done, definitely. This stuff is not working as well as it should. It's gotten us to this point, which is great, but it's not going to really survive the whole making enough gas to pressurize that room, the room above it, and eventually the room this is in, and that room, and yeah, we need a little bit more storage, we need some more sensible pipe routing, the ability to get the stuff a little bit easier. It's just all kind of a mess right now, so yeah, atmospherics is going to get reworked, but to do that, I mean, it's going to need a lot of stuff, and because it's going to need a lot of stuff, specifically need a lot of stuff built for it, we're going to need to work with this stuff a lot. And the improvements I've made to this with the vending machine and the automatic ingot routing and automatic output routing and stacker, it's great. It works awesome. It does wonders for my sanity. But it's not as good as it could be. We could have it, so we just push a button, and this machine sends the ingots it needs, and when it's done, it cycles everything back through, and it's clean, and it makes exactly the quantity that I want. All of that is possible, but the barrier is programming. Yep. Yeah, so to do a lot of this automation, to read the required inputs and all of that, we need to use IC10 and MIPS code. So MIPS is Stationeers' internal programming language. And we could do all of this using just the computer like we did out there. Actually, I did go fetch it in between while I was making some other stuff for this setup. But I then decided, you know what? We're going to be doing a lot of this stuff. I've already talked about some other MIPS programs. So let's just make ourselves a laptop. This little portable computer that we can use to build all of the stuff we need. Then let's also start by ripping up all of our floor, because we're going to need to get access to all of the wiring that exists over here for flooring. Yes. So, for this MIPS code, the goal of this program is going to be to read the required contents of our assemblers, so one for the Atmos, Electro, and auto lathe. Ooh, it looks cool. Does it need a battery or anything? I've honestly never used the Stationeers laptop. Yes, it needs a battery, it needs a motherboard, and it needs a programmable chip. Let's just use a little battery for now, and then if it's a pain, we'll change that later. And then for our motherboard, we're going to use the IC editor motherboard. And there we go. Oh, it saved the IC that it had in there before. Oops, I didn't want to put that away. But yeah, so our laptop is going to be what we use to actually do the programming. But first, we're going to have to get set up. So I've done a bit of trial and error experimentation to see how this is all going to work. Oh, that's cool. I like that. In a testing world. So to start, we're going to start with our electroprint, just because it's right here. So we need obviously an IC chip to be able to actually run the code. We're going to need a display unit to display what is going on, what ingots are required and requested, and what we've requested over here. A button to activate it, a dial to set the quantity that we want, and then it'd be nice to have a little status LED to show if something's wrong, what's going wrong, and all of that. So I did prepare some of this. I probably still have some things I need, but I've got our consoles, our IC housings, So let's just start by putting everything down. I figured we'll put our ICs right in front of everything. Hopefully the ICs don't actually stick out of the floor. I haven't tried that. They look kind of tall. Let's just see real quick. Otherwise I'll relocate them. Nope, they don't. Okay, excellent. Yes. So this one will also be a little bit of a tutorial on MIPS. I'm by no means a great expert on the system, but I like to think I know enough to be dangerous. And with MIPS specifically, I think I know a little more than the average Joe might about how the system works. And then we need to, I think we already have a power cable outside that is hooked into all of this from when our auto smelter was running off as well. So we'll head on out, and we're going to need to hook up our controls. Yeah. I can't wait till we have enough gas to actually pressurize all that. Yep, so we do have some cable out here already. Spin that a little ways, just in case we need it. Although theoretically we should just be able to run one cable up in each area. I'm glad I made some extra cables. And then alright, that should be everything. It should allow us to access everything. Let's head back in. So we're just laying the wires out where we're going to need them for our various controls to sit. So figure out our consoles. Now, if I was a bit more skilled, I will be the first to admit this, I probably could make this all work from 2 IC housings, maybe even 1, and I probably could make it work with just like 1 set of controls. I'm not quite that confident in my skills though, so we're going to need a dial. What the? It'll do. Is getting to these going to be a little bit of a pain? Probably. But hopefully not too much that it becomes annoying. We could also always move something to, like, right next to the manufacturing. Be the end of the world, but I don't think that that's too hard to get to. Unfortunately, it is a smidge cramped in this space. It'll be fine. If not, we'll move it around, but sure to be okay. Alright, so we've got all of the groundwork laid. For this one at least. Actually, we do need one more thing. I forgot. A hash display. 3 of those, because we need 3. Pop these into each of their respective spots. Electroprint's slightly taller than the rest of them. That is slightly annoying. Seal those up.
Hunger critical.
Super hungry. He's gonna die if I don't do something. We'll get to you in a moment. So, we also, just for our power consumption and probably cycle consumption rates, we are going to stick 2 logic circuits. Each of these... Alright. And finish up the wiring real quick. Boop. 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 Boop.
Hydration critical.
Alright. That now should be everything we need. Wired in and set up. Let's go eat and drink before I die. We've survived this thus far in this game. I don't plan on kicking the bucket anytime soon. Ooh, more potatoes. More food is always good. That is our most recent potato. This is our most damaged potato. A partial baked potato. Eat both of these, and they should be good to go. We're growing some new potatoes again. Oh, we actually did eat both of those. Alright, now we can get back to the exciting stuff of building complex systems and programming and all of that fun stuff. Before we can, though, we need to label some things. So vending machine is fine. That can stay as its current name. Each of these is fine. We're going to need to rename this console electro. In fact, we're going to basically tack this onto the end. Oops. The end of everything that is associated with the electroprint. And the stacker is fine as well. So now the electroprint stuff is named. Let's just do the auto lathe now. Hydraulic. Is it? I have to save my spelling. I'm a computer scientist, not a spelling expert. Dang it. I did the same thing again. Alright, and then last thing we should actually need to set up, I forgot about these, is the lights. I don't... Oh, jeez. Well, I'm glad we didn't try and pressurize that room. That would have been disappointing. I guess we forgot the upper glass in all of these. Whoops. Oh, sometimes I really wonder how I managed to make anything actually work. Well, I'm glad we noticed it before we tried to do the great pressurization. Yep. And I just fell off. Now this should be a sealed room. Oh, I guess all that testing of, oh, is this a sealed room now or not, didn't mean anything, because it wasn't. Well, now we can actually put our lights in. So these are just going to be kind of status lights. They help us see, come on, what is going on with each of our systems. LEDs. And we'll need to run some more wires, which means we'll probably need some more wires, actually. So let's just queue up some more cables. And start those. Soon I'll be able to just select, give me 50, and it will. But for now, we do with what we have. Labeler away. Now, theoretically, it's not like strictly required to have these, but I am not writing the script to handle optional devices right now. While possible, it's a bit of a pain in the neck, and I just don't want to deal with it. I'll be the first to say I'm not as good as the scriptwriter as some of the people who, like, made the scripts that run our furnace, but I know a thing or two. So I should be able to make something semi-competent. Especially, oh, exactly enough. Perfect. Alright, now we should have enough devices placed down that our scripts will function properly. So I will say, like with most of the things that I do on this specific world, I have a plan of what I want to do. I guess technically I didn't do this with the furnace. I had an exact, like, I need to do this, but that's mostly because I was copying someone else's design. With this, as like with everything else I've done on this world, which is, I think I know what I need to do. I've done a little bit of research to figure it out. But I am not not 100% sure. So we're going to learn together a little bit. Oh, that's not an autolathe. It's an LED autolathe. Jeez. There we go. So, our next favorite tool will be the screwdriver. So, well, actually, let's do some scripting first. So to do this, basically we need to write a custom script that allows us... So, in Stationeers, the way that things currently work is IC10 scripts can obviously interact with devices like they do with the furnace out there. Also, thank you to the comments section for letting me know that those scripts are pretty inefficient as far as computational time. because of the way that they get the device names. It's not the intended way it's supposed to work. But essentially, each of these IC housings has 6 devices that it can address using these 6 pinouts here. And then that allows it to read and write from devices in the world. So in our setup, we're going to read information from the electroprinter here, write information to, and read information from the button, the dial, write information to the LED, send information to our good old vending machine, and then these are some special, like, time-saving, not time, but cycle-saving solutions. So, how all of this is going to work. Let me think. Okay. So we're going to use our laptop here to write some custom IC10 code to interact with the electroprint, specifically the internal stack. So every come on, there we go. Here our current code. This is some of the code that was written before. So every IC10 script has a maximum length of 127 lines and a maximum width of, I'm not sure, I can't remember, but there's only so many characters you can put in a single line, and then a maximum size of 496 bytes. This is because these IC10s, unlike a lot of games where you have, like, say, Space Engineers programmable block where you're writing in a higher level language and it's doing very complex operations, the IC10s were always intended as a bit of a simplified programming system. So it helps keep the sim speed running high, but it also just somewhat limits what you can do, but it requires a little bit more thought. So this uses the MIPS programming language, which I kind of refer to as a simplified assembly. So to think about it, if you've ever seen assembly code, it's a very basic programming language that uses mostly operations like these to read and write from registers in memory or from the stack. I don't think we're going to need the stack in this particular example, but maybe if we do some upgrades to this in the future. But this will be the kind of first starting simplest version. So to start, we will initialize our system. So one of the things you can do that helps with MIPS programming over like traditional assembly is set up some aliases. So these are just string representations of specific memory or device registers. So we're going to start off with our fabricator, and this same code should work on all 3 of our fabricators, so I'm just going to be kind of generic in how I write it. So we'll call it a fab, and this will be device 0 for pin 0. Next up, we're going to have our vending machine. This will be device 1. Our button, so we're going to do our activate button. This will be device 2. So that's our first 3 devices. As with most things in computers, we start counting at 0, not 1. Then we're going to need our qtyDial. That's device 3. Our statusLED as device 4. And finally, our stacker as device 5. And just because I like things to be pretty, I'm just going to line up all our register numbers so they're nice in a line. Then we're going to set up our register names. So we're going to name a couple of specific numerical registers. I believe we have 16 to work with in MIPS. So R0 through R15, and then 16 and 17 are 2 special registers. which I'm not going to get into because they're not terribly important for this. So I'm going to treat these kind of like variables. So these are going to be my named registers. So our device, our active hash, or our, we're just going to call this, what should I call it? Let's say fabHash is going to be our 10. Our quantity actually let's shorten this to qty. It's going to be 11. neededHash is over. Our light color is going to be on 13. And off the top of my head, I think that's everything we need. So this handles setting up our aliases. And then the next section we're going to write is kind of our initialization. So the first time that the IC powers on, it's going to just set some stuff to certain statuses just to make sure everything is correct. So to do this, we use the set command. So let's do that. Part of init set. And now we're going to write to our devices. So we're going to first of all to make sure that our vending machine is on. So we're going to write to the on variable of our vending machine 1. So always write comments because it's not just the right thing to do, but it helps the next guy. And remember, the next guy is probably going to be you. Let's turn our stacker on. And 1 is, like with most things in computers, 1 is the binary true. So that's just saying, hey, we're turning this on. We're setting on to true. Now the stacker should already be on, but overwriting it shouldn't be an issue. Next up, we're going to make sure that our status LED is on. That's the last thing that I have to write to. And then we should actually set up our qtyDial as well. So set the qtyDial. What is it called? So one of the nice things you can do in Stationeers is in the Stationpedia. It has all of the logical inputs and outputs. So if I go to the dial, we can see that mode, I believe this is the max number, and then setting is the current number. And both of these are read-write. So set qtyDial, setting 1. And then we're going to set our max. So these we're treating 1 and 50 as actual numbers instead of binary true false. So some things to keep in mind. All right. All of that should be set up. So this is our kind of top end setup. So all of this code is only going to run once. In assembly, there is no like traditional for or while loops. You just have jump instructions. So in MIPS, we can do named jumps. So we can define segments of the program to either act as like variables, or not variables, but functions, or iterator, or not iterator, but loop points. So for this one, we are going to start our main loop here. So this will be our main loop, and we're going to call this main. So these little purple sections here are the kind of the jump points that we can return back to. So it will always know that, hey, wherever this is, anything that's a jump main will return to here, whether or not it moves up and down, instead of calling like an absolute line number like 22. So from here, we need to do a few things. So the kind of goal of this script is it's going to be broken up into a couple different sections. And I do have some notes here to remind me of what it does. So first of all, we need to get the required hash. So in each of these assemblers, so let me just confirm this real quick, but each of these manufacturers, so the Electroprint, the Autolathe, and all of them, they have kind of an internal memory. So if we actually just look real quick, electronics printer, and we go down through all of its resources used, its versions, manufacturers, logic. It has quite a lot of logic stuff, but like we can read the RecipeHash, we can read what reagents it has, but we can't actually read like what it requires directly. It won't just tell us like, I need an iron ingot. We have to use its internal memory. So each of these machines has an internal stack that we can either write to or read from. Using IC10, and the one we're interested in is this printer instruction missing recipe reagent opcode 9, and it says it's only valid from addresses 54 to 62. So these machines have 512 bytes of internal memory, and they have 63 addresses of internal space. So 0 to 63. And you can see each of these, there's a certain like number range. So for example, we are going to use this execute recipe command later on in the script. We need to write back to the memory of the machine, or yeah, we may use this. I don't remember if I actually used this yet, but I believe we do. We're going to write back to the machine, hey, the first 7 bits are going to be the opcodes. So for example, it's going to be opcodes 2. The next 8 through 15 bits will be the quantity that we need. And then bits 16 through 47 will be the prefab hash, which every machine has, or every thing in Stationeers has, right? So this is the prefab hash for the electronics printer. We're going to write the prefab hash, and then whatever's after that is unused. It doesn't care. We'll write those back to the machine, and that will tell the machine, hey, my memory's been updated. I need to execute this recipe. However, it will write to its own internal memory this command from addresses 54 to 62. So the opcode we don't really care about, but it's going to be opcode 9. Quantity ceiling, I don't really know what this variable does, and I haven't done enough investigation. I assume this is some kind of like quantity required, but I tried to use it like that and it didn't really work, so I kind of just ignore that right now. But what we're really interested in is 16 through 47, the reagent hash. This is what the machine actually needs in a reagent form. I'll get into the differences in a little bit, but the hash of the reagents that the machine requires to make the thing that it's trying to make. It will only write this, however, if it is trying to make something. So this is one of the reasons why we need to use some slightly more complex code to do this. But I'll get into that later on in the next segment of the script. But for now, the first part of this script is going to be read the required hash. So in our main loop, this will be get the required ingot hash. So we are going to get from R0 or we're going to store it in register 0. So I'm going to use register 0 through 9, because 10 is our fabHash, as kind of a temporary variable set. So if I need some temp variables, I'll use registers 0 through 9. But R0, our fabricator, and we're going to actually get from address 54. So, like I was saying, in the Stationepedia, this section starts at address 54, so that will be the start of the opcode. Next up, we are going to SRA, which I believe is a... also look here. So this one performs bitwise arithmetic right shift operation. So we're going to right shift a certain amount. So we're going to right shift 16 bits is what we need to do over and store that in our register R whatever. So we are going to store this in our neededHash. We are going to read it from R0. So R0 will have gotten everything from 54 to the end of the memory. And then we're going to actually move over the 16 bits that we need to get the reagent hash. Now, this is where the complexity comes in. So the reagent hash is not an ingot hash. The last step that we need to actually do to turn the reagent hash into the actual ingot hash is use the rmap function. So this basically is a way of interacting with the machine where it's given a specific reagent hash and it will return the prefab hash based on the device that it's given. So we'll just basically overwrite, in our case, the needed hash from the reagent hash. And this just looks like, oops.
Hydration critical.
That needed hash fab. So what we've done is we've gotten the 54th bit here. We move over 16 and get the remainder. So that's this line. So we get the 54th to the end, move over 16 bits. We store that in needed hash. Then we take the reagent hash and we give it the reference of we need the prefab hash of the reagent hash in the fabricator. So this is actually the section that gets the needed hash of whatever we're trying to make. So anything that the manufacturer is missing. I'm going to grab a drink real quick. Otherwise, my little guy is going to die. I may try and add a couple visuals to help illustrate this, but we'll see how editor me feels about that later on. Oops, shouldn't have done that. Dang it. I got so used to going in and out of these. Well, we can see that this room is now holding pressure. Oops. Hopefully that didn't tank the internal pressure. It shouldn't have. Oh well. Back to it. We are still surviving here, even though we're writing code. So from there, now we actually have our neededHash. Now this will only be populated with a number if the machine. So this gets, or of the machine. Sorry about that. This gets the prefab hash from the reagent hash based on the type of machine that we're actually getting the reagent hash from. All right. So that is kind of the section of the code that gets our ingot hash. Next up, we need a little quality of life thing that I like to put in. I guess it's not technically needed, but I want to show the recipe selected whenever something is not attempting to be made. So to do this, we are going to do a comparison operation. So what we're going to use is the bnez. So branch not equal actually we could just use bnez, branch not equal to 0. I didn't even notice that one before. Shows even I'm learning. So this is going to display the display fab display fabHash if the needed hash is clear. So this is going to branch not equal to 0. This is going to look at the needed hash, and it is going to branch somewhere. We don't actually have that branch yet. So essentially the way these branching commands work is if the conditions are satisfied, so in this case neededHash is not equal to 0, it will just execute a jump to that place. bnezal is a jump and return. So say we wanted to like call a function essentially, bnezal would be what we would use because this would store the next time in the RA register, which is the return address. So we could jump back to that return address upon completion of our function. We are not concerned about that in this case because we're running everything in a big loop, and it is okay if we don't do that. But we'll jump to somewhere else in a moment here, but the code that will run below this is going to be, we're going to load into our fabHash from our fabricator, the RecipeHash. So this will basically allow us to show, hey, this is the recipe we have selected when you go push the button. Then we're going to set our IC housings setting variable, which is kind of the like output variable of the whole IC housing. It's just called DB, which is the housing address. Our fabHash, so this will set that to that fabricator hash. And then we are going to actually move into our lightColor, so this will show a status. And for now, I think I'm going to use color dots yellow. So this basically is, hey, nothing's really being done. We're not actively making something, and we're not airing out. So all is good for now. And then we are going to jump somewhere else. Yeah, so the reason why we didn't want to use bnezAL here is because we don't actually want to run this code if we are not trying to. So if this actually does work, this isn't going to run. A bnezAL would be a execute this function and then return to line 30 and continue executing. So we'll leave that jump empty for now. The next section of this could be a function, but it doesn't need to be. So we're going to call this section request. So this will be an actual named section because this is where we're actually jumping to. So request, the reason I call this is because if the needed hash is not 0, that means that the system needs something. So we need to request it from the vending machine. So we are going to set our db variable. So we're going to set our housing setting variable to needed hash. This way that we can display, hey, we need iron ingots, we need copper ingots, we need all this other stuff. Even though we shouldn't actually have to do anything, it'll just keep us aware. We're going to set the vending machines request hash to needed. And actually, I want to look at the vending machine. So let's look at the IO kit interface options of the vending machine. So this is the request hash that we're going to use. Air might work. Not sure. We'll have to try that in a moment. This will be our first pass, like I said. Then, so we're going to request the thing we need, but we don't want to like queue a bunch of requests because this is going to run once every twice a second. So here also I need to as well vent my waste tank in my suit, otherwise my stationery is going to get very unhappy.
Waste tank critical.
The longer I talk, the more I have to do to keep myself alive. But essentially, we don't want to send another request because the way that these scripts work is they run once per tick when you use the yield, which we will do at the end of our loop, which basically means, hey, at the end of if there's time left in a game tick, hold on. But a game tick happens twice a second, so once every half second. We don't want to necessarily be sending these requests out once every half second because it does take some time to get the ingot from our vending machine and to our actual machine. So for now, I'm going to actually sleep. So sleep is just wait a number of seconds. Sure, yeah. Yep, I see for another number of seconds. We are going to sleep for 3 seconds. That's a good start. 3 seconds, and then this is going to be a name section called end request. So let's add some comments. Okay. Now this jump is actually going to be to end the quest. So we want to skip this section here if this runs. So you got to remember, like, even though this kind of looks like its own function definition, when the code runs, it runs top to bottom. It'll get here. If this is not equal to, if this is 0, it'll continue to line 30. It'll run this, this, this. If this jump wasn't here, it would then go to here and just keep running this. It doesn't skip these sections unless you have a jump that will specifically tell it to skip these sections. So by jumping to the end of the request block, it skips this code anytime this code runs. So next, after our request section runs, we need to check to see if our activate button has been activated. So this section is going to we are going to load from to our registry 1, so our secondary type temp variable. Probably could use R0 again. The setting, or no, not the setting. We are going to load R1 activate. How did I spell this up here? Activate. Active. 8. There we go. Now my stuff's out of alignment again. My neatness is my peril. Activate button, the setting. So this will show us our setting of the button, and then we are going to branch equal. So branch, if it is equal, R1 is equal to 1. And then we are going to branch to the assemble branch. We haven't wrote that yet, but that is where we're going to go. Otherwise, we are going to set the status LED color to our light color. So this will just display the current light color of whatever it should be. We are going to then yield. So that is the command I was talking about. So yield just waits till the end of the next game tick, and then jump back to main. So this is technically the end of our main loop. So this will jump back up to main and run through all of this again. This will run in its current state minus the error here. So next we need to actually write this section. So assemble. So this section is basically whatever. So then.
Air tank low.
Also, we should probably write our light color. Looking now, maybe my notes were wrong here. We should be writing our light color free. Every loop? Doesn't he wrote in every loop? Yeah, I guess it won't hurt. So we're going to actually just do that up here. So every time this thing loops through, it will set the light color appropriately. So in our assemble section, I don't think that'll break anything anyway. This section will actually be what writes to that internal memory to set our, tell the fabricator, build this even if you can't. And that's kind of the important part. because without the even if you can't section, so like just when you hit the activate button, it will actually just reject a command. But when we tell it build it even if you can't, it will actually start filling the neededHash section, so this up here, with the stuff that it needs. So that's why we need to do this. Section So our assembler's interface will still work for selecting recipes, but we're not going to use the activate button on the assembler. We're going to use the activate button on the wall. So the first thing that we're going to do is move lightColor color.green. So this will move our nice green color into the light, because this won't be running. Oh. Maybe I'm overcomplicating this whole light color thing. Maybe this should have been back under here. Probably. This should work. In fact, it's not that important. I think I'm going to choose a set down here. Set stat this LED. No, we are going to move the light color. I think this is the right way of doing it. Maybe. And then we're going to also immediately set the status LED, because it will reset back to the other color if we just did it with color. Maybe. Maybe I'm right, maybe I'm wrong, who knows. It's at least not a terribly important part of the program if it doesn't work correctly. So, now that we're at the assemble step, basically the first part of what we're going to do, just put a little comment here. Light, set, green. We are going to again get the current recipe hash, because we want to make sure we're assembling what is current. So we're going to to do this, we're going to load into our fabHash fabricator. Hash. Then next we're going to load into our quantity variable, the qtyDial setting. So this gets the recipe hash. Actually just tack that on the end to make it a little shorter.
Hunger
Quantity.
critical.
Oh, hit mine in. You're doing all right. So now we get to some of the more complex sections. Now we need to actually set up the instructions to our electroprint. Specifically, the first one we're going to use is the set device lock operator. So this one takes an opcode and a lock state as a Boolean. So to do this, we are going to, so essentially what we're doing is we're locking the device. So lock fab This way, no additional inputs can be made. So we're going to use the SLL, which is the logical load logical left, I believe. So SLL is the logical left shift operation. So we're going to do this into R1. We are going to, but we are using R1 already. This is R2. We're going to move 8 bits over. Then we are going to OR that. So we're going to do a logical OR operation. R1 with itself, with the print per instruction device set. I did not spell something correctly. Print per instruction device set lock. There we go. So this is an alias, or this is the actual name for the opcode. We could have also just used 6, but this makes it a little bit more readable. And for now, I'm going to also go get a potato, because I'm going to die without it. Yeah, we didn't take a terrible hit to our... internal... Oh, I just combined all those. Oops. Okay. Didn't mean to do that. All kinds of screw-ups in this episode. Alright. Now that we're not in immediate risk of dying, we should probably go fill up our pressure tank, though. So we are kind of in immediate risk of dying from that. Fresh. That's not a fresh tank of air. Pressure tank of air, but it's not actually filled to what it's supposed to be. That'll be good enough for now. Alright. Back to the wonderful laptop. Continue editing code. So we're writing the opcode of the set device lock into this. So we've moved the true Boolean statement, so the 1 for true, over 8 characters, and then we're ORing the opcode. This is building that instruction string. Or instruction number. And then we're going to put it, so using put, we can write to another device, to our fabricator, into address 0, the value of R2. So we're using R2, not R1. Next up, we need to tell the printer to wait until the next valid recipe to not move on. So we're going to OR into R2. We're just kind of reusing it again. 0 into printer instruction dot wait until next valid. Then we're going to put that into our fabricator at address 1 R2. This actually, I think, is false. So if we look, wait until next valid. Yeah, so we are... Oh, it's nothing. It's just the opcode. So by writing the opcode, we are selling it. Hey, wait. Next up, we are setting the quantity and hash for the execute recipe command. So we are going to look at our instructions again, and execute recipe is opcode 2, so we need to write the prefab hash, the quantity, and the opcode. So to do this, we are going to, first of all, SLL, so logical left, to R3, actually, our quantity at position 8. Then we're going to logical left. Or no, this can go into, yeah, we'll use R3. This one will go into R4, our hash, into position 16, our fabHash. There we go. Capitalization is important. So essentially each of these, and I'll try and show a graphic on the screen if I can put one together that makes sense. We're loading R3, our quantity, 8 characters or 8 positions over. We're loading our fabricator hash at R4, 16 positions over. So if we look at our system here, the 8th position is where our quantity goes. The 16th position is where the prefab hash goes. So we haven't set the opcode yet because we're going to OR all of these together. And by logical ORing each of these together, we're basically flattening each of these variables. So we're quite literally going to do that now. We're going to do an OR, and we're going to OR our R3 with R4. Or we're going to OR R3 into R3, R3 and R4. Then we're going to OR R3 with R3. So ORing itself into itself. Because this is where we're storing it. This is what we're ORing in our first position, and in our second position, we're going to use another printer instruction. Dot execute P S S S P. There we go. And then from there, we write that to the fabricator into its second position, or not defab, fab into its second position in its stack, and then R3. So each of these, right, so we're writing this into the first position in its memory, the second position in its memory, the third position in its memory. It's going to kind of keep going on like this because it'll run these in sequence. So it'll first lock it, then it'll wait till next valid, then it will do the requested recipe, and then we keep going from there. So because the printer will actually run at a different timing than this. It's not going to try and do this and then continue execution. This will run regardless of whether the printer has completed whatever it's doing. And that's actually to our benefit because that's how we get the code up here to work. Next up, after the printer has actually built the thing that we want it to build, we are going to tell it to dump all of its reagents out because we don't need them anymore. So we're going to OR with R2 again. I'm kind of breaking these up a little bit because I don't want to overwrite something important, even though after this put is taken place, technically whatever's in here doesn't matter anymore, but it's just kind of a sanity thing for me. Sorry if it bothers you. With 0, printer instruction dot react agents. And so this is going to get ingots. Put fab 3 R2. And then finally, we're going to unlock the device. R2. Eight. That just kind of empties out R2. 4. R2 with store in R2, R2. Printer. Device. That's block. So we're setting it to false. That's what we're doing. That's right. So in the 8th position, we're storing logical false. Put fabricator. 5th position, R2. Then we're going to yield here because we've skipped our typical end of the loop. Yield there, and then jump to. So that theoretically is all the code we need, I think. Let me just do a quick sanity check and check each section. So we start up, we alias everything, we set up our initial instructions, so we turn everything on, we set up our quantityDial, we do our main loop, so we get our required ingot hash, we display a fabricator hash if the needed hash does not exist. If a needed hash does exist, we jump to our request. We request the vending machine. From the vending machine, our needed hash. We wait for that to actually arrive. I'm going to increase this to 5 seconds. It takes a while for some of our stuff to move. If this is 0, we're going to set our light color to yellow. We're going to jump to our end request here, which is just going to wait for the activate button. If the activate button is not 0, it's not 1, we're going to set our status LED to the correct light color. Then we're going to yield and jump to main. If it is 1, we are going to jump to assemble, which is going to queue all of the instructions into the assembler to do the assembling things. And our light color might be a little messed up, unfortunately. I don't know if there's a great way that I can fix that. Well, I can move this, actually. Move this to right there. Maybe. Hopefully. I think that'll work. But we can now confirm this and yeah, it's just laptop. So we can export that. Now we have some stuff written to a thing. We're going to dump that in there. Now we're going to use our screwdriver to set up all of this stuff. So we'll turn you on. First of all, turn this on. It'll flash an error, but that will now set our stuff up. So we'll turn it off now. So fabricator is going to be the electronics printer. Our vending machine is going to be vending machine. Our activate button is going to be button electroprint. QuantityDial is going to be dial electroprint. Our status LED is going to be LED electroprint, and our stacker is just going to be the stacker. Oh no, we did forget something. I forgot to actually set up the stacker. We'll do that in a second here. Let me just do this real quick. So the reason I have these extra logic chips is because I don't want this to just run while this is off, because we're going to have 3 of them here. These will turn this off whenever this is not on. So for our reader, we're going to select our electronics printer. We're going to select power. And then from this, we're going to select the logic reader electroprint. And we are going... Oh, these are all logic readers. Well, oops. This needs to be a logic writer. In is going to be the logic reader electroprint. Out is going to be IC housing electroprint, and out there is going to be the on value. Hey, our light is yellow, but we actually need to yank that real quick because I forgot a section. So when we do all this, when we set our light color, we want to also never set our quantity. Oh no, we set our quantity here. Okay, here we go. So we're going to set our stacker. I don't remember what the name is, but stacker, we can look it up pretty easily. This is going to be the setting, I believe. So stacker setting to qty. That should be the last thing that I need to do. Export, grab that, dump that in there. And then we also are going to need our data disk real quick. And we're going to try and finagle our data disk into our console real quick. This is going to be the IC housing. Electroprint. Boop. Okay, so now we can see our electroprint is showing us the thing we actually ordered, and let's see if we can... Is there more settings on here that I just can't see? No. Okay, whatever, that's fine. Showing us the thing we're ordering. We can set our quantity. So should we give it a try? I'd say so. We've got a cable coil, a quantity of 1. Everything should be set up. Let's actually, we have a bunch of stuff in here, so let's purge all that first. That would be an unfair test. Go. Everything should be back in the vending machine. When we press our button, light turns green for a moment. Stuff gets ordered. Cable coil gets made. And this spits out a whole bunch of cable coils because it got set to 1. We already had a bunch of cable coils in here. Oops. Well, there's a hazard. Theoretically, that shouldn't happen in the future. But, and now it shouldn't have anything left in its... It still does. And it's also still locked. Oh, why didn't you work? Let's push it again. And now it did it right. Okay. That was a bit odd. But it seems to have worked after the second shot. So, one moment while I replicate this across to the rest of the assemblers. Alright. I've set up the other 2 machines, so now each of these ICs should be all set up and ready to go. Before I put the floor back down, I did realize one thing. Technically, I didn't need these logic leaders because I actually already have them over here, but oops, I'm going to leave them. I already set it up, and I don't want to change it now. Yes, it requires slightly more power, but yeah, it's negligible in the grand scheme of things, I think. But let's just make sure it all works. Because I don't want it to just not. So, we'll turn on our auto lathe. And let's see. I want... What do I want? I would like... a... Let's see. I actually want... I know what I want. A cable kit for upstairs. So instead of hitting build up here, we've got it selected there. We want this. No, that seems to be correct. It just didn't get set for some reason. Let me just make sure the dial is set correctly. It is. We want one.
Hydration critical.
Activate. Needs iron ingots. Needs copper ingots. Building the thing. We need to fix the status LED code. And we've got one table. We can now turn... No, it didn't unlock. Why are you being a fuss? Why is it not unlocking? What line are you stuck at? Because you should unlock. That's the 4th statement. Like, if I look, it's now happened twice for debugging hell. Eject all reagents, which it did, and then unlock the device. 3 and 4. We're using R2. Like, I can't even select something else. So we're just going to build another table, I guess. Or I guess I can set the quantity to 0. See how this horribly breaks it. Boop. Well, that unlocked it at least. It's just weird that it didn't unlock it automatically. Let's select something else, maybe. Fuel sheets. Let's say we want... $25. Boop. Push the button. Press the steel ingots. Yeah. Oh, that's weird. I mean, we found a kind of solution, so I'm not terribly upset, but let's see. Electroprint, I want to make a... I actually want to make something here. I want a beacon. Make me one. That's right. We're gonna use gloves. That. It is cool that that just works. Cycles everything back into the system. Now we can turn it off. I wonder if it's just the first time it airs out. We're going to build this somewhere, eventually. It's all good. It's emptied out. Probably pipe bender. More grading. Confident it's working. You know that before putting the floor back down. Let's see. I want a marked gas canister. Use that button. Gonna take some getting used to. Oh, it's just a zero. 5 seconds might be a little long as well. Yeah, it still needed silicon, so it was able to request the second stack. Checked everything out, and it unlocked itself. Very strange. Yeah, seems to work. So we've further improved our Automagic setup here by increasing its level of automation, by making it so we can just order whatever we want. And I'm gonna actually die of thirst. Thank you all for watching. This has been an awesome video. I hope you've enjoyed. I feel like I did something good here. Hopefully you learned something about MIPS programming and that it's a little bit more approachable. I'll be doing some more with it soon. And thank you all for watching, and I hope you have enjoyed. Remember to leave a like and subscribe if you have. Send me a comment if you notice something I did wrong or something I can do better. And I will see you all next time.